Hi, welcome back. This probably will be a little quickie of a section because it's very short. We're going to continue what we did in section 5.2. We're going to keep developing the definite integral by looking at a Riemann sum. So remember, the idea was that if we had some sort of positive continuous function, and we wanted to find its area underneath the curve from x is equal to a to x is equal to b, what we did is we partitioned that region into n equally spaced x's. We've decided that by dividing the interval from a to b into n equal spaces. The width of each interval was given by b minus a, right endpoint minus left point, divided by the number of subdivisions. Then we drew a rectangle up from each endpoint and made a decision to go with either a right endpoint to give you the height or the left. The picture I've drawn gives you the right endpoint. The value of the function at each of the right endpoints is the height of each rectangle, and then the width is delta x. So the overall area is the sum of the areas of however many rectangles you decide to draw. The idea is that the more rectangles you put into your region, the better your approximation is. So if you start with 4 rectangles, if you double that and make A, you'll have a better approximation. Double that with 16 rectangles, have a better approximation, and so on. So you just keep making the number of rectangles larger and larger and larger, and you'll get closer and closer and closer to the actual area. Now with calculus, we can do that with a limit. We can set up a general series of functions of heights times widths, and then take a limit as n goes to infinity. And as we do that, as n goes to infinity, the width of each subinterval gets smaller and smaller and smaller until it's essentially the width of a line segment. And we have this entire region colored in with an infinite number of line segments. Since the width of each rectangle is getting really small, it doesn't matter if we use a left sum or a right sum. So I'm just going to denote that we have some sort of special xk star, as giving us the location of the height. F of xk star is the height of the rectangle, and delta x is the width. And then when you take the limit, as n goes to infinity, delta x is going to go to 0, and this becomes the exact area under the curve. And what you saw in the last section was that that exact area, it has some relationship between our indefinite integral that we've talked about in section 5.1, and we're going to call that integral, the exact area integral, a definite integral. And we write it as the integral of f of x with respect to x from x is a to x is b. The a and the b are called the limits of integration. The function whose area we seek will be called the integrand, but it's the height of each rectangle. The dx is the width, and so we've got an integral sign, the integral of f with respect to x from x is a to x is b. We require the function to be positive and continuous, but we're going to see that that positive stuff doesn't matter. But we know that all continuous functions will have an integral. Some not continuous functions will, depending, but all continuous functions have an integral. So I've drawn you a continuous function down a bit. I drew a horizontal line. And if you are going to interpret the integral of some constant with respect to x, then it's finding the area underneath that horizontal line from x is a to x is b. That's just the area of a rectangle, width times height. Well, the height is k, and the width is b minus a. So the integral of any constant with respect to x is that constant times b minus a. If we don't go anywhere in our integral, if we're integrating a function beneath a single point, then there's no thickness. And the area beneath a single point then is going to have a value of 0. The next one says that if I integrate a function from a to b, where a is on the left of b, you get the same thing as if you integrate the function from b to a, but it will be opposite in sign, because what we're doing is we're subtracting differently to get the width. A minus b and b minus a have the same difference, but opposite in sign. And then we've got a partitioning property that if you want to integrate from x is a to x is b, and you have some intermediate point c, then you can find the integral from a to c, which is the area from a to c, add it to the area from c to b, and you'll get the same area as if you went just straight from a to b. So here's some little short examples. We're going to interpret these as area. So in problem number 1, we're finding the area beneath the curve y is equal to 4x. From x is 0 to x is 3. When x is 0, y is 0. When x is 3, y is 4 times 3 is 12. That's a straight line. And so I'm asking you to find the area of this right triangle. The area of a right triangle is 1/2 base times the height. Well, the base width is 3 units. The height is 12. So this area should be 1/2, 3 times 12. 3 times 12 is 36. 1/2 of 36 is 18. Now here's where I let you in on the secret. Remember that this had something to do with finding the antiderivative of 4x. The antiderivative of 4x is the function whose derivative is 4x. So that's going to be a 2x squared plus some constant. That we called capital F in the last section, the antiderivative. If we find the value of the antiderivative at the right endpoint minus the value of the antiderivative at the left endpoint, we should get that same area. So let's try it. 2 times 3 squared plus c minus 2 times 0 squared plus c. 3 squared is 9. 2 times 9 is 18. This c subtracts out with that c, and 2 times 0 is 0. And so that is the way you can use calculus to compute that area. You find the antiderivative, and then you find the values of the antiderivative at the upper limit of integration minus the value of the antiderivative at the lower limit of integration. That's going to be called the fundamental theorem of calculus, but that raises its head in the next section. Now in the next one, we can't use calculus to integrate this. We don't know how to integrate the square root of 4 minus x squared. But we do know that this thing is area under a curve, so all we've got to realize is that this thing here represents the area of the top half of the circle, right? If y is equal to 4 minus x squared, under the square root sign, then y squared is 4 minus x squared, and then I can rearrange the terms to get the circle. I know it's the top half because we took the square root. So it's a circle, top half of a circle anyway, of radius 2. So this should give us the same as the area of the top half of a circle of radius 2. Well, the area of a whole circle is pi r squared. And since it's just half of it, we multiply it by half. And now I said the radius was 2. So inside the parentheses I get 4 pi. Half of 4 pi is 2 pi. So the value of this definite integral is 2 pi because it gives us the area of the top half of a circle. Now in example 3, I have a random function. Let me draw a picture here. Some random continuous function. And from -2 to 1, we're told that area is equal to 2. And from 1 to 4, we're told that that area is equal to 8. So if you want to get the area from -2 all the way out to 4, doesn't it make sense that that's just going to be 2 plus 8? That's that addition rule, that the area from -2 to 1 plus the area from 1 to 4 is the area from -2 to 4. That's what we just did right here, but the picture tells you the obvious. Part B wants us to find the area from 4 back to 1. So since we're reading it backwards, this should be the same as minus the area from 1 to 4. We always read from left to right, so if you read here from right to left, then you change the sign. Then the integral from 1 to 4 was 8, so the integral from 4 to 1 is -8. Finally, in part C, the area underneath a single point is going to be defined by 0 because the width of that one rectangle is 0. There's the properties of the definite integral. Okay, now let's see if this one makes sense. Now we've got two different functions, both of them integrated from 0 to 2. That the integral from 0 to 2 of f of x is 5, so that's the area under that curve, and the area under the g of x function is 3. We saw that an indefinite integral has a linearity property that you can integrate term by term in a sum, and if you have constants, you can pull them out. Well, the same idea is going to apply here. I can rewrite this as two separate integrals. And we can pull constants out. Then we have the values of each of those integrals. This should be 2 times 5, and g of x was 3, minus 4 times 3, and so we get 10 minus 12 is -2. So we have the linearity property of the definite integral, just like what we have for the indefinite integral. You can integrate term by term through a sum or difference, and you can pull constants out. So our big plan is in the next section. We're going to have our big theorem that says that if you want to compute a definite integral from a to b of some function, then you need to know its antiderivative. Antiderivative means that the derivative of capital F gives you little f. Once you find the antiderivative, you replace the x with the numbers on the integral sign, and then that number gives you the value of the definite integral, where that interpretation of that value is that it's area under the curve, or we can even be more general. For instance, if f is velocity, then its antiderivative is position, and this would represent the total change in position, or the displacement of an object. If f measures something, then this is antiderivative is the total change or the sum in the antiderivative of little f. And that's going to be called the first fundamental theorem of calculus. So that's going to be next section, but here we just set the groundwork. So there's not much in this section, just get a little practice at doing your approximation integrals with rectangles, and you learn the properties of the definite integral.